The universe is vast, mysterious, and filled with secrets that defy our understanding. What if I told you that there are forces at work in the cosmos so strange, so inexplicable, that even the brightest minds in science are left scratching their heads? Today, we're diving into the unknown, exploring 25 of the most baffling space anomalies that challenge everything we think we know about the universe. And at the heart of this cosmic mystery lies the dark flow phenomenon, a force so enigmatic that it hints at something beyond the edges of our observable universe. What could be pulling entire clusters of galaxies in a single direction, defying the laws of physics as we know them? The answers might just rewrite the rules of reality itself. So, buckle up and prepare to journey into the depths of space, where the unknown awaits and the mysteries of the cosmos unfold. By the end of this video, you'll not only uncover the secrets of the dark flow phenomenon, but also discover why the universe is far stranger than we ever imagined. Let's begin. Now, let's dive into the first and perhaps one of the most perplexing mysteries of the cosmos, the dark flow phenomenon. Discovered in 2008 by a team of scientists analyzing data from the Wilkinson microwave anisotropy probe, this phenomenon revealed something utterly bizarre. Clusters of galaxies spread across vast regions of space were found to be moving in a specific direction at incredible speeds that couldn't be explained by the gravitational pull of any known matter in the observable universe. It's as if something invisible, something beyond the edges of what we can see, is tugging at these galaxies with an unseen force. So, what exactly is the dark flow? Imagine the universe as a vast ocean with galaxies floating like ships on its surface. Now, picture all those ships being pulled in the same direction by a current that no one can see or explain. That's the essence of the dark flow, a mysterious, large-scale motion of galaxy clusters that defies our current understanding of physics. Scientists estimate that this flow extends billions of light years, far beyond the boundaries of the observable universe. But here's the kicker. According to our current models, the universe is supposed to be uniform and isotropic, meaning it should look the same in all directions. The dark flow challenges this fundamental assumption, suggesting that there's something out there, something massive and unknown, that's influencing the motion of galaxies on a scale we can barely comprehend. This anomaly raises profound questions. Could there be other universes beyond our own, exerting gravitational influence on ours? Or is there a colossal structure hidden from our view that's pulling everything toward it? The dark flow phenomenon doesn't just challenge our understanding of the universe, it hints at the possibility that our cosmic neighborhood is just a small part of a much larger, more mysterious reality. And as we continue to explore this enigma, one thing is certain: the universe is far stranger and far more complex than we ever imagined. Now, let's explore the theories that scientists have proposed to unravel the mystery of the dark flow. One of the most intriguing ideas is the existence of other universes beyond our own. This concept, rooted in the multiverse theory, suggests that our universe might be just one of many, each with its own unique properties. If this is true, the gravitational pull from a neighboring universe could be influencing the motion of galaxy clusters, creating the dark flow we observe. It's a mind-bending idea, but it offers a potential explanation for why these galaxies are moving in such a coordinated way, seemingly against the rules of our known universe. Another compelling theory points to the possibility of massive, unseen structures lurking in the cosmic shadows. These structures, often referred to as superclusters or cosmic filaments, could be composed of dark matter, a mysterious substance that makes up a significant portion of the universe's mass but doesn't interact with light. If such structures exist beyond the observable universe, their immense gravitational influence could be the unseen force driving the dark flow. This theory aligns with the idea that the universe is far more complex than we currently understand, with hidden layers waiting to be uncovered. Some researchers have even speculated that the dark flow could be evidence of a cosmic imbalance left over from the early universe. During the Big Bang, the universe expanded rapidly, but it's possible that this expansion wasn't perfectly uniform. Tiny irregularities in the distribution of matter could have grown over billions of years, creating large-scale flows like the dark flow. This theory ties the phenomenon back to the very origins of the cosmos, suggesting that the seeds of this mystery were planted long before galaxies even formed. While these theories offer fascinating possibilities, none have been definitively proven. The dark flow remains one of the most tantalizing puzzles in modern astrophysics, challenging us to rethink our understanding of the universe's structure and its boundaries. As we continue to gather data and refine our models, one thing is clear: the answers, when they come, will likely reshape our view of reality itself. And with that, let's turn our attention to another cosmic enigma, the Great Attractor, a gravitational anomaly that's pulling galaxies toward it with an irresistible force. Now, shifting our gaze to another cosmic mystery, we encounter the Great Attractor, a gravitational anomaly so powerful that it's pulling entire galaxies toward it, including our own Milky Way. Imagine a force so immense that it defies our understanding of the universe's structure. This enigmatic region, located roughly 250 million light-years away, lies in the direction of the constellations Centaurus and Hydra. Despite its overwhelming influence, the Great Attractor remains shrouded in mystery, largely because it sits behind the plane of our galaxy, obscured by dust and stars. What makes the Great Attractor so fascinating is its role in the cosmic web, the vast, interconnected network of galaxies, gas, and dark matter that forms the backbone of the universe. This web isn't random. It's shaped by gravity, with dense regions like the Great Attractor acting as hubs that draw in surrounding matter. Scientists believe that the Great Attractor isn't just a single object but a concentration of mass, possibly a supercluster of galaxies, whose combined gravitational pull is bending the paths of galaxies across vast distances. But here's where it gets even more intriguing. The Great Attractor isn't the end of the story. Beyond it lies an even larger structure known as the Shapley supercluster, which may be exerting its own gravitational influence. This suggests that the Great Attractor itself might be moving, pulled by something even more massive. It's like a cosmic tug-of-war with galaxies caught in the middle, racing toward an unseen finish line. The mystery deepens when we consider what lies within the Great Attractor. Observations suggest it contains thousands of galaxies, but its exact composition and the source of its immense gravitational power remain unclear. Some scientists speculate that dark matter, the invisible substance that makes up most of the universe's mass, could be playing a key role. Others suggest that the Great Attractor might be part of a larger, undiscovered structure, hinting at even greater complexities in the cosmic web. What's clear is that the Great Attractor challenges our understanding of the universe's large-scale structure. It reminds us that even as we map the cosmos, there are still vast regions of space that remain hidden, waiting to be explored. And as we continue to study this gravitational giant, we may uncover clues not just about its nature, but about the forces that shape the universe itself. With that in mind, let's turn our attention to another cosmic puzzle, the Fermi paradox, a question that has puzzled scientists and dreamers alike. If the universe is so vast, where is everyone? Now, as we venture into the realm of cosmic questions, we arrive at one of the most thought-provoking mysteries in the universe, the Fermi paradox. Named after the physicist Enrico Fermi, this paradox highlights a striking contradiction. Given the vastness of the cosmos and the high probability of extraterrestrial life, why haven't we found any evidence of it? It's a question that has puzzled scientists, philosophers, and dreamers for decades, and it challenges our assumptions about life beyond Earth. To understand the Fermi paradox, let's start with the numbers. Our galaxy alone, the Milky Way, contains hundreds of billions of stars, many of which are orbited by planets. With such an unimaginable number of worlds, it seems almost certain that some of them should host life, perhaps even intelligent civilizations. And yet, despite decades of searching through radio signals, space probes, and telescopes, we've found nothing. No signals, no artifacts, no signs of advanced civilizations. This silence is what makes the Fermi paradox so perplexing. One possible explanation is that intelligent life is incredibly rare. Perhaps the conditions needed for life to evolve and thrive are so specific that they're almost impossible to replicate. Or maybe civilizations tend to self-destruct before they can develop the technology to communicate across the stars. Another theory suggests that advanced civilizations might exist, but they're so far beyond our understanding that we simply can't recognize their presence. They might be using technologies or forms of communication that are completely alien to us, but the Fermi paradox isn't just about the absence of evidence. It also raises profound questions about our place in the universe. If we're truly alone, what does that mean for humanity? Are we a cosmic accident, or is there something uniquely special about our existence? On the other hand, if intelligent life is out there, why haven't we made contact? Are they avoiding us, or are we simply not looking in the right way? The implications of the Fermi paradox extend far beyond curiosity. For space exploration, it serves as both a challenge and a motivation. If we're to find answers, we'll need to push the boundaries of our technology and expand our search for life. Missions to distant planets, advanced telescopes, and new methods of communication could all play a role in solving this cosmic riddle. And even if we don't find extraterrestrial life, the search itself could lead to discoveries that transform our understanding of the universe. As we ponder the Fermi paradox, we're reminded that the universe is full of mysteries waiting to be unraveled. It invites us to question, to explore, and to dream. And with that, let's turn our attention to another enigmatic signal from the cosmos, the WOW signal, a brief but tantalizing glimpse of something that might just be out there. Now, shifting our gaze to another cosmic enigma, we encounter the WOW signal, a fleeting yet electrifying moment in the history of space exploration. Detected on August 15, 1977, this mysterious radio signal has captivated scientists and enthusiasts alike, standing as one of the most compelling pieces of evidence in the search for extraterrestrial intelligence. The story begins at Ohio State University's Big Ear Radio Telescope, where astronomer Jerry Amon was scanning the skies for signs of intelligent life. As the telescope swept across the constellation Sagittarius, it picked up a signal so powerful and unusual that Amon circled it on the printout and wrote, "Wow." Next to it, a name that has stuck ever since. The signal lasted for 72 seconds, the maximum duration the telescope could observe a single point in the sky, and it matched the characteristics scientists had predicted for an artificial extraterrestrial transmission. What made the WOW signal so extraordinary was its intensity and frequency. It was 30 times stronger than the background noise of space and appeared at a frequency of 1,420 MHz, a range often considered ideal for interstellar communication because it's relatively free from interference. These details fueled speculation that the signal could have originated from an intelligent source, possibly a distant civilization attempting to make contact. Despite its tantalizing nature, the WOW signal has never been detected again, despite numerous attempts to find it. This has led to a range of theories about its origin. Some suggest it could have been a natural phenomenon, such as a comet or a burst of cosmic energy, while others argue it might have been a one-time transmission from an advanced civilization. The lack of a definitive explanation only adds to its mystique, making it a cornerstone of discussions about extraterrestrial life. The WOW signal's significance extends beyond its mystery. It serves as a reminder of the challenges and possibilities in the search for extraterrestrial intelligence. While it didn't provide conclusive proof, it demonstrated that our tools and methods are capable of detecting potential signals from beyond our world. This has inspired ongoing efforts to refine our technology and expand our search, from projects like the Search for Extraterrestrial Intelligence or SETI, to new initiatives using advanced telescopes and artificial intelligence. As we reflect on the WOW signal, we're reminded of the vastness of the cosmos and the tantalizing possibility that we're not alone. It's a call to keep looking, to keep listening, and to remain open to the extraordinary. And with that, let's turn our attention to another cosmic puzzle: fast radio bursts, or FRB, bursts of energy that are as mysterious as they are powerful. Now, as we venture deeper into the cosmos, we encounter another phenomenon that has left scientists scratching their heads: fast radio bursts, or FRB. These are incredibly brief but intensely powerful bursts of radio waves that originate from deep space, lasting only a few milliseconds. Yet, in that fleeting moment, they release as much energy as the sun does in an entire day. First discovered in 2007, FRBs have since become one of the most intriguing and perplexing mysteries in modern astrophysics. What makes FRBs so fascinating is their unpredictability. Most of these bursts are one-off events detected only once and never observed again. However, a small number of them have been found to repeat, sending out multiple bursts over time. This repetition has provided scientists with valuable clues, but it has also deepened the mystery. Why do some FRBs repeat while others don't? And what could possibly generate such immense energy in such a short span of time? The origins of FRBs remain a hotly debated topic. Some theories suggest they could be produced by highly magnetized neutron stars, known as magnetars, which are capable of releasing enormous amounts of energy in sudden bursts. Others propose that FRBs might result from cataclysmic events, such as the collision of two neutron stars or the collapse of a black hole. There's even speculation that they could be signals from advanced extraterrestrial civilizations, though this idea remains highly speculative and lacks concrete evidence. One of the biggest challenges in studying FRBs is their sheer distance. These bursts come from galaxies billions of light years away, making it difficult to pinpoint their exact sources. Despite this, astronomers have made significant strides in recent years. Advanced telescopes and detection methods have allowed us to identify the host galaxies of some FRBs, providing crucial context for understanding their origins. Yet, even with these breakthroughs, the true nature of FRBs continues to elude us. What's particularly exciting about FRBs is their potential to reveal new insights about the universe. Because these bursts travel such vast distances, they interact with the cosmic material they pass through, leaving behind subtle clues about the structure and composition of the universe. By studying FRBs, scientists hope to learn more about the distribution of matter in space, the properties of intergalactic magnetic fields, and even the rate at which the universe is expanding. As we continue to unravel the mystery of fast radio bursts, one thing is clear: they represent a frontier of discovery in astrophysics. Each new detection brings us closer to understanding these enigmatic signals, while also reminding us of how much we still have to learn about the cosmos. And with that, let's turn our attention to another cosmic oddity: the Boötes Void, a vast and eerily empty region of space that challenges our understanding of the universe's structure. Now, shifting our gaze to another cosmic enigma, we arrive at the Boötes Void, a region of space so vast and empty that it defies our expectations of how the universe should look. Stretching across an area of space roughly 330 million light-years in diameter, the Boötes Void is one of the largest known voids in the observable universe. Unlike most regions of space, which are teeming with galaxies, stars, and cosmic structures, this void is eerily sparse, containing only a handful of galaxies where thousands would typically be found. The existence of the Boötes Void challenges our understanding of the universe's large-scale structure. According to the standard model of cosmology, matter in the universe is distributed in a web-like pattern, with dense clusters of galaxies connected by filaments and separated by vast, empty regions known as voids. However, the Boötes void is far emptier than most voids, raising questions about how such a colossal emptiness could form. Some scientists suggest that it might be the result of smaller voids merging over billions of years, creating a single, massive region of emptiness. Others propose that it could be linked to the early universe's conditions, where fluctuations in density led to the formation of such extreme voids. What makes the Boötes void particularly intriguing is what it reveals about the universe's evolution. By studying its structure and the few galaxies within it, astronomers can gain insights into how matter is distributed on the largest scales. The void's existence also provides a unique testing ground for theories about dark energy, the mysterious force driving the universe's accelerated expansion. Some researchers speculate that the Boötes void could be a region where dark energy's effects are more pronounced, influencing the distribution of matter in ways we don't yet fully understand. Despite its emptiness, the Boötes void is not entirely devoid of interest. The galaxies that do exist within it are often isolated, with fewer neighbors than galaxies in denser regions. This isolation makes them fascinating subjects for study, as their evolution and behavior may differ significantly from galaxies in more crowded parts of the universe. Some of these galaxies appear to be unusually bright, suggesting that they may have formed under unique conditions or interacted with the void's environment in unexpected ways. The Boötes void serves as a reminder of how much we still have to learn about the cosmos. Its vast emptiness challenges our assumptions and pushes us to refine our models of the universe's structure and history. As we continue to explore this mysterious region, we may uncover new clues about the forces that shape the cosmos and the intricate balance between matter and emptiness. With that, let's turn our attention to another cosmic anomaly, the Pioneer Anomaly, an unexplained deceleration of spacecraft that has puzzled scientists for decades. Now, as we venture further into the cosmos, we encounter a mystery that has left scientists scratching their heads for decades: the Pioneer Anomaly. This peculiar phenomenon involves the unexpected deceleration of the Pioneer 10 and Pioneer 11 spacecraft as they journeyed through the outer reaches of our solar system. Launched in the early 1970s, these spacecraft were designed to explore the outer planets and beyond, but their trajectories revealed something strange. Instead of continuing to coast through space as predicted by our understanding of gravity, both spacecraft experienced a tiny but consistent slowing down, as if an unseen force was gently tugging them back. The Pioneer Anomaly was first noticed in the 1980s when scientists analyzing the spacecraft's telemetry data found that they were deviating slightly from their expected paths. This deviation was incredibly small, just a fraction of a nanometer per second squared, but over the vast distances these spacecraft traveled, it added up to a significant discrepancy. At first, researchers considered mundane explanations, such as the possibility of gas leaks or thermal radiation from the spacecraft's power systems. However, after extensive analysis, none of these factors could fully account for the anomaly. This left scientists with a tantalizing question: was there something fundamentally wrong with our understanding of gravity, or was there an unknown force at play in the depths of space? The implications of the Pioneer Anomaly are profound. If our current models of gravity, based on Einstein's theory of general relativity, are incomplete, it could mean that there are aspects of the universe's fundamental forces that we have yet to discover. Some theories have proposed that the anomaly could be evidence of dark matter or dark energy influencing the spacecraft, while others have suggested modifications to the laws of gravity itself. These ideas remain speculative, but they highlight how even the smallest discrepancies can lead to groundbreaking questions about the nature of the cosmos. Interestingly, the Pioneer Anomaly has not been observed in other spacecraft such as Voyager 1 and Voyager 2, which followed similar trajectories. This has led some researchers to speculate that the anomaly might be unique to the design of the Pioneer spacecraft, possibly due to the way they radiate heat or interact with the solar wind. However, this explanation has not been universally accepted, and the mystery remains unresolved. What makes the pioneer anomaly so captivating is its reminder that even in the vastness of space, the smallest details can hold the keys to unlocking profound mysteries. It challenges us to question our assumptions and pushes the boundaries of our knowledge. As we continue to explore the cosmos, anomalies like this serve as humbling reminders of how much we still have to learn. With that, let's turn our attention to another cosmic oddity, the Oumuamua mystery, an interstellar visitor that has sparked debates and speculation about its origins and nature. Now, shifting our gaze to a visitor from beyond our solar system, we encounter the enigmatic Oumuamua. This mysterious object, first detected in October 2017, holds the distinction of being the first known interstellar object to pass through our cosmic neighborhood. Its arrival sparked both excitement and intrigue as scientists scrambled to study its peculiar characteristics and unravel its origins. Oumuamua, which means scout or messenger from afar in Hawaiian, immediately stood out due to its unusual shape and behavior. Unlike typical asteroids or comets, Oumuamua appeared elongated, resembling a cigar or a pancake, with estimates suggesting it was about 10 times longer than it was wide. Adding to the mystery, it exhibited a reddish hue, a trait often associated with organic rich materials found in the outer reaches of solar systems. But what truly baffled researchers was its motion. As it traveled through our solar system, Oumuamua accelerated in a way that couldn't be explained by gravity alone, leading to speculation about its composition and the forces acting upon it. One of the most debated aspects of Oumuamua is its origin. Some scientists propose that it could be a fragment of a larger object, perhaps shattered by a collision in another star system. Others suggested it might be a comet, though it lacked the telltale coma, a cloud of gas and dust that typically surrounds comets as they approach the sun. Intriguingly, its acceleration hinted at the possibility of outgassing, where volatile materials on its surface vaporize and propel the object forward. However, no such outgassing was directly observed, leaving this explanation incomplete. The lack of clear answers fueled even more imaginative theories. Some researchers speculated that Oumuamua could be an artificial object, perhaps a piece of alien technology or a solar sail designed to harness the pressure of sunlight for propulsion. While this idea captured the public's imagination, most scientists remained skeptical, emphasizing the need for natural explanations. Yet, the possibility of an interstellar artifact, however remote, underscores the profound questions Oumuamua raises about the nature of objects traveling between star systems. What makes Oumuamua so fascinating is not just its unusual characteristics, but also what it represents: a glimpse into the vast, uncharted territories beyond our solar system. Its brief visit reminded us that the cosmos is teeming with objects we have yet to discover and understand. As we continue to explore the universe, Oumuamua serves as a tantalizing hint of the mysteries that await us in the interstellar void. With that, let's turn our attention to another cosmic puzzle, the Kuiper Cliff, a sudden and unexplained drop-off in objects at the edge of our solar system. Now, as we venture further into the outer reaches of our solar system, we encounter a puzzling boundary known as the Kuiper Cliff. This mysterious feature marks a sudden and dramatic drop-off in the number of objects beyond a certain point in the Kuiper Belt, a region filled with icy bodies and dwarf planets like Pluto. The Kuiper Belt itself is a vast expanse stretching from the orbit of Neptune out to about 50 astronomical units from the Sun. But beyond this point, the population of objects seems to plummet, leaving scientists scratching their heads. The Kuiper Cliff is particularly intriguing because it defies our expectations. Based on our understanding of how the solar system formed, we would expect the number of objects to gradually decrease as we move further out. Instead, the Kuiper Cliff presents a sharp and unexpected boundary, almost as if something has swept the area clean or prevented objects from accumulating beyond this point. This abrupt change has led to a variety of theories attempting to explain its existence. One leading hypothesis suggests that the Kuiper Cliff could be the result of gravitational interactions with an unseen planet. This idea ties into the broader search for Planet 9, a hypothetical world thought to exist in the distant reaches of our solar system. If such a planet exists, its gravitational pull could have disrupted the orbits of objects in the Kuiper belt, creating a clear boundary where fewer objects remain. While this theory is compelling, the elusive nature of Planet 9 means it remains unproven, leaving the Kuiper Cliff as an unsolved mystery. Another possibility is that the Kuiper Cliff marks the outer edge of the primordial disk of material from which the solar system formed. In this scenario, the sharp drop-off could simply reflect the natural limits of where material was able to accumulate during the early stages of the solar system's formation. However, this explanation raises its own questions, as it doesn't fully account for why the transition is so abrupt rather than gradual. Some researchers have also proposed that the Kuiper Cliff could be the result of collisions or interactions with passing stars. Over billions of years, our solar system has likely encountered other star systems, and these close encounters could have stripped away objects from the outer Kuiper belt. While this idea is plausible, it's difficult to test as it relies on events that occurred long ago and left little direct evidence. What makes the Kuiper Cliff so fascinating is not just the mystery of its existence, but also what it tells us about the dynamic and ever-changing nature of our solar system. It serves as a reminder that even in our own cosmic backyard, there are still secrets waiting to be uncovered. As we continue to explore the Kuiper belt and beyond, the Kuiper Cliff stands as a tantalizing clue, urging us to look deeper and question what we think we know about the universe. With that, let's turn our attention to another cosmic anomaly, the axis of evil, a peculiar alignment in the cosmic microwave background radiation that challenges our understanding of the universe's structure. Now, shifting our gaze from the outer edges of our solar system, we turn to a cosmic mystery that lies far beyond the axis of evil. This peculiar alignment in the cosmic microwave background radiation, or CMB, has puzzled scientists since its discovery. The CMB is essentially the afterglow of the Big Bang, a faint echo of the universe's birth, and it holds crucial clues about the early universe. But the axis of evil, as it's dramatically named, presents a strange and unexpected pattern that challenges our fundamental understanding of cosmology. The cosmic microwave background radiation is remarkably uniform, but it does contain tiny fluctuations that reveal the seeds of galaxies and galaxy clusters we see today. These fluctuations are supposed to be random, reflecting the chaotic nature of the early universe. However, the axis of evil refers to a peculiar alignment of these fluctuations along a specific plane in the sky. This alignment suggests a kind of order or structure that shouldn't exist according to the standard model of cosmology, which assumes the universe is isotropic or the same in all directions. What makes this alignment so baffling is that it defies the principle of isotropy, a cornerstone of modern cosmology. If the universe is truly isotropic, there should be no preferred direction or axis. Yet, the axis of evil hints at a possible directionality, raising questions about whether our understanding of the universe's structure is incomplete. Some scientists have even speculated that this alignment could be evidence of something beyond our current models, such as the influence of another universe or a pre-Big Bang structure. One theory suggests that the axis of evil could be the result of gravitational waves from the early universe, which might have imprinted a directional pattern on the CMB. Another idea is that it could be a statistical fluke, a random alignment that appears significant simply because we're looking at it from a particular vantage point. However, the persistence of this pattern across multiple observations makes the fluke explanation less convincing, leaving scientists searching for a more robust explanation. The implications of the axis of evil are profound. If this alignment is real and not just an artifact of measurement, it could force us to rethink some of the most fundamental assumptions about the universe. It might even hint at new physics, such as modifications to Einstein's theory of general relativity, or the existence of dimensions beyond the four we currently understand. For now, though, the axis of evil remains one of the most tantalizing and controversial mysteries in cosmology. As we continue to probe the cosmos, anomalies like the axis of evil remind us that the universe is far more complex and mysterious than we often assume. They challenge us to question our assumptions and push the boundaries of our knowledge. With that in mind, let's move on to another enigmatic phenomenon, the Black Knight satellite, a supposed mysterious object orbiting Earth that has sparked both scientific curiosity and wild conspiracy theories. Now, let's turn our attention to a story that has captivated both scientists and conspiracy theorists alike: the Black Knight satellite. This enigmatic object, said to be orbiting Earth, has been the subject of countless theories, ranging from extraterrestrial technology to secret government projects. But what exactly is the Black Knight satellite, and how much of its story is rooted in fact versus fiction? The tale of the Black Knight begins in the late 1950s, when reports surfaced of an unidentified object detected in orbit around Earth. Some claimed it was an alien satellite sent to observe humanity, while others suggested it was a relic of an ancient advanced civilization. The name Black Knight itself evokes a sense of mystery and intrigue, fueling imaginations and inspiring countless speculative stories. One of the most famous pieces of evidence cited by believers is a series of unusual radio signals allegedly picked up by Nikola Tesla in the late 19th century. Tesla, a pioneer in electrical engineering, reported receiving strange, repeating signals that he believed could have originated from an extraterrestrial source. Decades later, these signals were retroactively linked to the Black Knight, though no concrete evidence supports this connection. Another key moment in the Black Knight's lore came in 1960, when the United States Navy reported tracking an unknown object in polar orbit. At the time, this was highly unusual, as human-made satellites typically orbited the equator. This discovery sparked speculation that the object could be of extraterrestrial origin. However, it was later revealed to be debris from a Discoverer satellite, part of a classified military program. Despite these explanations, the myth of the Black Knight persisted, fueled by photographs and videos that purportedly show the object in orbit. One widely circulated image, often cited as evidence, was later identified as a thermal blanket lost during a spacewalk. Yet, the allure of the Black Knight continues, with many dismissing these debunkings as cover-ups or misinformation. So, why does the Black Knight satellite endure as a cultural phenomenon? Part of its appeal lies in its ability to tap into our fascination with the unknown and the possibility of extraterrestrial life. It also reflects a broader skepticism toward official narratives, with some viewing the Black Knight as evidence of hidden truths about our place in the universe. While the Black Knight satellite remains a compelling story, it's important to separate fact from fiction. Scientific evidence overwhelmingly points to human-made origins for the objects associated with the myth. Yet, the enduring mystery of the Black Knight reminds us of humanity's enduring curiosity and our desire to uncover the secrets of the cosmos. With that in mind, let's shift our focus to another cosmic enigma, Tabby's star, a celestial object whose unusual dimming patterns have sparked theories of alien megastructures and other extraordinary phenomena. Now, let's journey to a star that has puzzled astronomers and sparked imaginations worldwide: Tabby's star, also known as KSE 8462852. Located roughly 1,400 light-years away in the constellation Cygnus, this star gained fame for its bizarre and unpredictable dimming patterns, which some have speculated could be evidence of alien megastructures. But what's really going on with this enigmatic star? The mystery began in 2015 when citizen scientists analyzing data from NASA's Kepler Space Telescope noticed something unusual. Tabby's star was dimming in irregular and dramatic ways, with its brightness dropping by as much as 22% at times. This was far more extreme than the typical dimming caused by planets passing in front of a star, leading to widespread speculation about what could be causing such drastic changes. One of the most intriguing theories proposed that the dimming could be caused by a Dyson sphere, a hypothetical megastructure built by an advanced alien civilization to harness energy from their star. This idea captured the public's imagination, turning Tabby's star into a focal point for discussions about extraterrestrial life. However, scientists were quick to point out that while the idea was fascinating, it was far from the only possible explanation. Researchers have since explored a range of natural explanations for the star's behavior. One leading theory suggests that the dimming could be caused by a massive cloud of dust and debris orbiting the star. This dust could be the remnants of a shattered planet or comet, creating irregular patterns as it passes in front of the star. Another possibility is that the star itself is undergoing internal changes, such as fluctuations in its magnetic activity, which could affect its brightness. To better understand Tabby's star, astronomers have conducted extensive observations using ground-based telescopes and space observatories like Hubble. These studies have revealed that the star's dimming is not uniform across all wavelengths of light, which supports the idea that dust rather than solid structures is the likely culprit. Dust particles scatter shorter wavelengths of light more effectively, creating a distinctive signature that matches the observations. Despite these findings, the allure of the alien megastructure theory persists, partly because it taps into our fascination with the possibility of intelligent life beyond Earth. Tabby's star serves as a reminder of how much we still have to learn about the universe and the strange phenomena that inhabit it. While the evidence currently points to natural causes, the star's unusual behavior continues to inspire curiosity and drive scientific inquiry. As we move forward, the story of Tabby's star highlights the importance of keeping an open mind while rigorously testing hypotheses. It's a perfect example of how science balances imagination with evidence, always striving to uncover the truth behind the mysteries of the cosmos. And speaking of cosmic mysteries, our next stop takes us to the heart of the Milky Way, where an unexplained glow of gamma rays has left scientists scratching their heads, the galactic center excess. Now, shifting our gaze to the very heart of our galaxy, we encounter another cosmic enigma. The galactic center excess. Nestled at the core of the Milky Way, this mysterious phenomenon is characterized by an unexplained glow of gamma rays, the most energetic form of light in the universe. First detected by NASA's Fermi Gamma Ray Space Telescope, this excess of gamma radiation has puzzled scientists for years, sparking a quest to uncover its origins. At the center of our galaxy lies a supermassive black hole, surrounded by a dense cluster of stars, gas, and dust. While some gamma rays are expected from these sources, the observed levels far exceed what current models predict. This discrepancy has led researchers to explore a variety of potential explanations, ranging from mundane astrophysical processes to more exotic possibilities involving dark matter. One leading hypothesis suggests that the excess gamma rays could be produced by a population of rapidly spinning neutron stars known as millisecond pulsars. These incredibly dense remnants of dead stars emit powerful beams of radiation as they rotate, potentially contributing to the observed glow. However, the sheer number of pulsars required to account for the excess has made this explanation difficult to confirm, leaving room for alternative theories. Another compelling possibility ties the galactic center excess to dark matter, the elusive substance that makes up about 85% of the universe's mass. According to some theoretical models, dark matter particles could collide and annihilate each other, releasing gamma rays in the process. If this is the case, the excess could provide a rare glimpse into the nature of dark matter, offering clues about its properties and interactions. To test these ideas, scientists have conducted detailed analyses of the gamma-ray data, searching for patterns that could point to specific sources. For instance, if the excess were caused by dark matter, the gamma rays would likely be distributed smoothly across the galactic center. On the other hand, if pulsars were responsible, the gamma rays would appear as distinct point sources. So far, the evidence remains inconclusive, with some studies favoring one explanation over the other, but no definitive answer has emerged. The galactic center excess serves as a reminder of how much we still have to learn about the universe's most fundamental components. Whether it's the result of pulsars, dark matter, or something entirely unexpected, this phenomenon continues to challenge our understanding of the cosmos. As researchers refine their models and gather more data, the mystery of the gamma-ray glow may eventually yield groundbreaking insights into the nature of our galaxy and the universe at large. With this cosmic puzzle still unresolved, our journey through the unexplained anomalies of space takes us next to another perplexing discrepancy: the Hubble tension, a growing rift in our understanding of the universe's expansion rate. Now, as we venture further into the mysteries of the cosmos, we arrive at a puzzling rift in our understanding of the universe itself: the Hubble tension. This phenomenon revolves around a growing discrepancy in how fast the universe is expanding, a fundamental measurement that shapes our entire understanding of cosmology. The story begins with Edwin Hubble, the astronomer who first discovered that the universe is not static but expanding. This groundbreaking revelation laid the foundation for the Big Bang theory and our modern understanding of the cosmos. To measure the rate of this expansion, scientists use a value known as the Hubble constant. However, here's where things get intriguing. Two of the most reliable methods for calculating this constant, observations of nearby celestial objects and measurements of the cosmic microwave background radiation, are yielding different results. On one hand, observations of nearby stars, supernova, and other cosmic markers suggest a faster expansion rate. On the other, data from the early universe captured by missions like the Planck satellite point to a slower rate. This inconsistency, known as the Hubble tension, has left scientists scratching their heads. How can two highly precise methods, both grounded in solid physics, produce such conflicting results? One possibility is that there's an error in our measurements or calculations, though repeated checks have yet to uncover any significant mistakes. Another, more exciting explanation is that the discrepancy points to new physics, something beyond our current understanding of the universe. For instance, it could hint at the existence of unknown particles or forces, or even a deeper complexity in the nature of dark energy, the mysterious force driving the universe's accelerated expansion. The implications of resolving the Hubble tension are profound. If it's due to new physics, it could revolutionize our understanding of the cosmos, potentially rewriting the rules of cosmology. On the other hand, if it's a matter of refining our measurements, it would still represent a significant step forward in our ability to map the universe's evolution. As scientists continue to gather data and develop new techniques, the Hubble tension remains one of the most pressing challenges in modern astrophysics. It's a reminder that even our most fundamental assumptions about the universe are subject to scrutiny and revision. And with that, we turn our attention to another cosmic mystery, the missing baryon problem, where a significant portion of the universe's normal matter seems to have vanished without a trace. Now, shifting our gaze to another cosmic puzzle, we encounter the missing baryon problem, a mystery that challenges our understanding of the universe's most basic building blocks. Baryons, the particles that make up ordinary matter like protons and neutrons, are the stuff of stars, planets, and even us. Yet, when scientists tally up all the baryons in the universe, a significant portion seems to be missing. The story begins with the Big Bang, which produced a specific amount of baryonic matter. Based on this, scientists can predict how much of this matter should exist in the universe today. However, when they count the baryons in stars, galaxies, and gas clouds, the numbers don't add up. A staggering amount of baryonic matter, roughly 30 to 40%, appears to be unaccounted for. So, where could this missing matter be hiding? One leading theory suggests that it exists in the form of a diffuse, hot gas spread throughout the vast regions of space between galaxies. This gas, known as the warm-hot intergalactic medium, is incredibly difficult to detect because it's so thin and emits very little light. However, recent observations using advanced telescopes and techniques have started to reveal faint traces of this elusive material. Another possibility is that the missing baryons are tied up in structures we haven't yet observed, such as cosmic filaments, the massive threads of gas and dark matter that form the cosmic web. These filaments, which connect galaxies across the universe, could contain vast reservoirs of baryonic matter that have so far evaded detection. The implications of solving the missing baryon problem are significant. Not only would it complete our inventory of the universe's ordinary matter, but it would also provide crucial insights into the formation and evolution of cosmic structures. Understanding where and how baryons are distributed could shed light on the processes that shaped galaxies and the large-scale structure of the universe itself. As researchers continue to refine their methods and develop new technologies, the search for the missing baryons remains a key focus in astrophysics. It's a reminder that even the most fundamental aspects of the cosmos can hold surprises, and that our journey to understand the universe is far from over. With that, we turn our attention to another enigmatic feature of the cosmos, the cold spot in the cosmic microwave background, a region of space that defies explanation. Now, as we venture deeper into the cosmos, we come across a peculiar anomaly that has left scientists scratching their heads: the cold spot in the cosmic microwave background. This mysterious region, located in the constellation Eridanus, is significantly colder than its surroundings, and its existence challenges our understanding of the universe's early moments. The cosmic microwave background, or CMB, is the afterglow of the Big Bang, a faint radiation that fills the entire universe. It provides a snapshot of the universe when it was just 380,000 years old, offering clues about its infancy. Normally, the CMB is remarkably uniform, with only tiny fluctuations in temperature, but the cold spot stands out as a glaring exception, a patch of space that's about 70 microkelvin colder than the average. So, what could cause such a dramatic temperature drop? One leading theory suggests that the cold spot might be the imprint of a cosmic void, a vast, empty region of space where matter is unusually sparse. As light travels through such a void, it loses energy due to the expansion of the universe, a phenomenon known as the integrated Sachs-Wolfe effect. This could explain why the cold spot appears colder than its surroundings. However, not everyone is convinced. Some researchers argue that the cold spot is too large and too cold to be explained by a void alone. Instead, they propose that it could be evidence of something far more exotic, like a collision with another universe. According to this idea, our universe might be just one of many in a multiverse, and the cold spot could be the scar left by a collision with a neighboring universe. While this theory is speculative, it opens up fascinating possibilities about the nature of reality itself. Another intriguing explanation ties the cold spot to the early universe's quantum fluctuations. These tiny ripples in the fabric of space-time, amplified by cosmic inflation, could have created regions of varying density and temperature. The cold spot might simply be an unusually large fluctuation that survived the universe's rapid expansion. Despite the competing theories, one thing is clear: the cold spot is a reminder of how much we still have to learn about the cosmos. It challenges our models of the universe's formation and evolution, pushing scientists to rethink their assumptions and explore new ideas. As we continue to study this enigmatic feature, it may reveal secrets not just about the cold spot itself, but about the fundamental nature of the universe. With this mystery still unresolved, we now turn our attention to another cosmic oddity, the Eridanus supervoid, a vast, empty region of space that might hold the key to understanding the cold spot and other anomalies in the cosmic microwave background. Now, shifting our gaze to another cosmic enigma, we encounter the Eridanus supervoid, a colossal region of space that seems almost unnaturally empty. Stretching across an astonishing 1.8 billion light-years, this supervoid is one of the largest structures ever discovered in the universe. But what makes it truly fascinating is its potential link to the cold spot we just explored, raising questions about the very fabric of our cosmos. The Eridanus supervoid is a region where galaxies and matter are strikingly sparse, creating a vast emptiness that defies our expectations of how the universe should look. Scientists believe that such voids form as a result of the universe's large-scale structure, where matter clumps together in some areas and leaves others nearly barren. But the sheer size of the Eridanus supervoid makes it an outlier even among other cosmic voids. One of the most intriguing aspects of this supervoid is its possible connection to the cold spot in the cosmic microwave background. As light travels through the universe, it interacts with the matter and energy it encounters. When light passes through a void, it loses energy due to the universe's expansion, a process known as the integrated Sachs-Wolf effect. This energy loss could explain why the cold spot appears colder than its surroundings, as the Eridanus supervoid might be acting as a cosmic lens, distorting the light that passes through it. However, the connection between the supervoid and the cold spot is not without controversy. Some researchers argue that the supervoid is too small to fully account for the cold spot's temperature drop, suggesting that other factors might be at play. Could there be additional voids or structures we haven't yet detected? Or does this discrepancy hint at something even more profound, like a flaw in our understanding of gravity or the nature of dark energy? The Eridanus supervoid also challenges our models of cosmology. If voids of this size are more common than we thought, it could mean that the universe's large-scale structure is far more complex than current theories predict. This raises questions about the distribution of matter and the forces that shape the cosmos on the grandest scales. Are we missing a piece of the puzzle, or is there a deeper, hidden order to the universe that we have yet to uncover? As we ponder these questions, the Eridanus supervoid serves as a reminder of how much we still have to learn about the universe. It's not just an empty patch of space, it's a window into the mysteries of cosmic structure and evolution. By studying this supervoid and its potential connection to the cold spot, scientists hope to uncover new insights into the forces that govern our universe, from the smallest quantum fluctuations to the largest cosmic structures. With this exploration of the Eridanus supervoid, we've only scratched the surface of its mysteries. But as we move forward, we'll delve into another cosmic puzzle that has captivated astronomers for decades, the dark matter mystery, a phenomenon that shapes the very fabric of the universe yet remains invisible to our eyes. Now, as we venture deeper into the cosmos, we encounter one of the most perplexing mysteries of all dark matter. This invisible substance makes up about 85% of the universe's total mass, yet it eludes direct detection, leaving scientists to piece together its existence through its gravitational effects. Imagine a cosmic puppeteer, unseen but undeniably powerful, shaping the movements of galaxies and the very structure of the universe itself. That's the role dark matter plays, and its mystery has captivated astronomers for decades. The story of dark matter begins with observations that didn't quite add up. In the 1930s, astronomer Fritz Zwicky noticed that galaxies within the Coma cluster were moving much faster than expected based on the visible matter alone. He proposed the existence of Dunkelmaterie, or dark matter, to explain this discrepancy. decades later, Vera Rubin's groundbreaking work on galaxy rotation curves provided further evidence. She found that stars at the edges of galaxies were orbiting just as fast as those near the center, defying the laws of gravity as we understood them. The only explanation, an invisible mass exerting its gravitational pull. But what exactly is dark matter? Despite its name, it's not simply dark in the sense of being non-luminous. It doesn't emit, absorb, or reflect light, making it completely transparent to our telescopes. This invisibility has made it one of the most challenging puzzles in modern astrophysics. Scientists have proposed various candidates for dark matter, from weakly interacting massive particles or WIMP to actions and even primordial black holes. Yet, despite decades of searching, no direct evidence has been found, leaving its true nature shrouded in mystery. One of the most compelling pieces of evidence for dark matter comes from gravitational lensing. When light from distant galaxies passes through a massive object like a galaxy cluster, its path is bent by the object's gravity. But sometimes the amount of bending observed far exceeds what the visible matter can account for. This suggests the presence of additional mass, dark matter acting as an unseen lens. Observations like these have allowed scientists to map the distribution of dark matter across the universe, revealing a vast cosmic web that underpins the structure of everything we see. Despite its invisibility, dark matter's influence is everywhere. It's the scaffolding upon which galaxies form and grow, the glue that holds galaxy clusters together, and the force that shapes the large-scale structure of the universe. Without it, the cosmos as we know it wouldn't exist, yet its very nature remains one of the greatest unsolved questions in science. Why hasn't it been detected directly? Is it because our current technology isn't advanced enough, or is dark matter something entirely different from what we've imagined? The search for dark matter continues, with experiments deep underground in space and at particle colliders around the world. Each new discovery, or lack thereof, brings us closer to understanding this elusive substance. Could dark matter be a particle yet to be discovered, or does it hint at a deeper, more fundamental truth about the universe? As we grapple with these questions, one thing is certain. Dark matter is not just a missing piece of the puzzle, it's a gateway to a deeper understanding of the cosmos. With dark matter still cloaked in mystery, our journey through the unexplained anomalies of space continues. Next, we'll explore another force that shapes the universe in ways we're only beginning to comprehend: the enigma of dark energy, the mysterious driver behind the universe's accelerating expansion. Shifting our gaze from the invisible scaffolding of dark matter, we now turn to another cosmic mystery that defies explanation: dark energy. This enigmatic force is responsible for the universe's accelerating expansion, a discovery that shook the foundations of cosmology in the late 1990s. Imagine the universe as a balloon, not just expanding, but doing so faster and faster over time. That's the effect of dark energy, a force so pervasive that it makes up about 68% of the universe's total energy content. Yet, despite its dominance, we know almost nothing about what it truly is. The story of dark energy begins with a surprising observation. In 1998, two independent teams of astronomers were studying distant supernova to measure the rate of the universe's expansion. They expected to find that the expansion was slowing down due to gravity's pull. Instead, they discovered the opposite: the universe was expanding at an accelerating rate. This revelation was so unexpected that it earned the teams the Nobel Prize in Physics in 2011, the only explanation for this acceleration. A mysterious force now called dark energy, pushing galaxies apart. But what exactly is dark energy? Unlike dark matter, which exerts a gravitational pull, dark energy seems to act as a kind of anti-gravity, driving the universe apart. One leading theory suggests that dark energy is a property of space itself, often referred to as the cosmological constant, proposed by Albert Einstein over a century ago. The cosmological constant was initially introduced to balance the equations of general relativity, though Einstein later dismissed it as his greatest blunder. Ironically, it may now be the key to understanding dark energy. Another possibility is that dark energy is a dynamic field known as quintessence, which changes over time and space. Yet, despite these theories, its true nature remains elusive. The implications of dark energy are profound. If the universe continues to expand at an accelerating rate, distant galaxies will eventually move so far away that their light will never reach us. Over billions of years, the universe could become a vast, empty expanse with galaxies isolated from one another. This scenario, known as the Big Freeze, paints a stark picture of the cosmos's future. But dark energy's behavior is still uncertain. Could it change over time, leading to a different fate for the universe? Or is it a constant force destined to drive expansion forever? Efforts to understand dark energy are ongoing, with projects like the Dark Energy Survey and the upcoming Euclid Space Telescope aiming to map its effects on the universe's large-scale structure. By studying the distribution of galaxies and the cosmic microwave background, scientists hope to uncover clues about dark energy's nature. Yet, like dark matter, it remains one of the greatest mysteries in modern science. Is dark energy a fundamental property of space, or is it something entirely new, waiting to be discovered? As we ponder the mysteries of dark energy, we're reminded of how much we still have to learn about the universe. Its discovery has reshaped our understanding of cosmology, revealing a cosmos that is not only expanding but doing so at an ever-increasing pace. What other secrets does the universe hold? As we continue our journey through the unexplained anomalies of space, we'll next explore the phenomenon of galactic cannibalism, a process that shapes the evolution of galaxies in ways both violent and beautiful. Now, let's turn our attention to a cosmic phenomenon that's as dramatic as it sounds: galactic cannibalism. This process, where larger galaxies devour smaller ones, plays a crucial role in shaping the universe as we know it. Picture a cosmic dance where galaxies, bound by gravity, interact in ways that can be both destructive and transformative. Galactic cannibalism is one of the most striking examples of these interactions, and it reveals a lot about how galaxies grow and evolve over billions of years. At the heart of galactic cannibalism is gravity, the invisible force that governs the universe. When two galaxies come close enough, their gravitational pull can draw them together. The larger galaxy, with its stronger gravitational field, begins to strip stars, gas, and dust from the smaller one. Over time, the smaller galaxy is completely absorbed, its material becoming part of the larger galaxy. This process doesn't happen overnight. It can take hundreds of millions or even billions of years, but the results are spectacular. The larger galaxy grows in size and mass, often gaining new stars and even entire star clusters from its smaller companion. One of the most famous examples of galactic cannibalism is our own Milky Way. Astronomers have discovered evidence that our galaxy has consumed smaller galaxies in the past. For instance, the remnants of a dwarf galaxy, known as the Sagittarius Dwarf Spheroidal Galaxy, are currently being absorbed by the Milky Way. This ongoing process is leaving behind streams of stars and gas, which trace the path of the smaller galaxy as it's pulled apart. Similarly, the Andromeda Galaxy, our nearest galactic neighbor, has also been observed consuming smaller galaxies. In fact, Andromeda and the Milky Way are on a collision course themselves, set to merge in about 4.5 billion years. When that happens, the resulting galaxy will be a product of galactic cannibalism on a massive scale. But galactic cannibalism isn't just about destruction, it's also about creation. When galaxies merge, the collision can trigger bursts of star formation. The gas and dust from the smaller galaxy compress under the gravitational forces, leading to the birth of new stars. These starbursts can light up the merging galaxies, creating some of the most luminous objects in the universe. Over time, the chaotic interactions settle down, and the merged galaxy takes on a new, often more complex structure. This process is a key driver of galaxy evolution, shaping the diversity of galaxies we see today. Interestingly, galactic cannibalism also has implications for the supermassive black holes at the centers of galaxies. When two galaxies merge, their central black holes can eventually spiral toward each other and collide, releasing enormous amounts of energy in the form of gravitational waves. These collisions are some of the most energetic events in the universe, and they provide valuable insights into the nature of black holes and gravity itself. As we explore the phenomenon of galactic cannibalism, we're reminded of the dynamic and ever-changing nature of the cosmos. It's a universe where even the largest structures are in constant motion, interacting in ways that shape their futures. From the birth of new stars to the merging of supermassive black holes, galactic cannibalism is a testament to the power of gravity and the intricate dance of galaxies across the universe. With this understanding of galactic cannibalism, we're ready to delve into another cosmic mystery: the enigmatic nature of quasars, the brightest objects in the universe. What makes them shine so intensely, and what secrets do they hold about the early universe? Let's find out. Now, shifting our gaze to one of the most dazzling phenomena in the cosmos, we encounter quasars, celestial powerhouses that outshine entire galaxies. These enigmatic objects are not just bright, they are the brightest entities in the universe, radiating energy at levels that defy comprehension. But what exactly are quasars, and how do they produce such staggering amounts of light and power? Let's unravel the mystery. Quasars, short for quasi-stellar radio sources, were first discovered in the 1960s. Initially, they appeared as faint, star-like points of light, but their radio emissions revealed something far more extraordinary. We now know that quasars are the intensely luminous cores of distant galaxies, powered by supermassive black holes. These black holes, millions or even billions of times more massive than our Sun, are surrounded by swirling disks of gas and dust. As material from these disks spirals into the black hole, it heats up to extreme temperatures, releasing vast amounts of energy in the form of light, radio waves, and other radiation. This process makes quasars visible across billions of light years, acting as cosmic beacons in the depths of space. One of the most intriguing aspects of quasars is their connection to the early universe. Because light takes time to travel, the quasars we observe today are actually glimpses into the distant past. Many of them existed when the universe was just a fraction of its current age, providing crucial insights into how galaxies formed and evolved. Their immense brightness allows astronomers to study the conditions of the early universe in remarkable detail, shedding light on the processes that shape the cosmos as we know it. But the mysteries surrounding quasars don't end there. Despite their incredible energy output, the exact mechanisms behind their formation and behavior remain topics of intense research. For instance, how do supermassive black holes grow to such enormous sizes so quickly in the early universe? What triggers the inflow of material into these black holes? And why do some quasars emit jets of particles traveling at nearly the speed of light? These questions continue to challenge our understanding of physics and the universe. Adding to the intrigue, quasars are not just relics of the past. Some are still active today, though they are much rarer in the modern universe. This decline in quasar activity over time suggests that the conditions necessary for their formation and sustenance have changed dramatically. Understanding why this shift occurred could reveal important clues about the life cycle of galaxies and the role of supermassive black holes in shaping their evolution. As we explore the mysteries of quasars, we're reminded of the universe's capacity for both beauty and complexity. These luminous giants not only illuminate the distant reaches of space, but also challenge us to rethink our understanding of physics, time, and the very fabric of reality. With each discovery, we come closer to unraveling the secrets of these cosmic powerhouses and the role they play in the grand tapestry of the universe. Next, we'll turn our attention to another cosmic anomaly, neutron star glitches, sudden changes in their rotation rates that defy expectations. What causes these strange behaviors, and what can they teach us about the nature of matter under extreme conditions? Let's dive in. Now, let's venture into the strange and unpredictable world of neutron stars, where even the most stable objects in the universe can experience sudden, unexplained changes. These cosmic oddities, known as neutron star glitches, are sudden shifts in the rotation rates of these incredibly dense stellar remnants. Imagine a spinning top that suddenly speeds up or slows down without warning. That's essentially what happens during a neutron star glitch. But what causes these bizarre events, and what do they tell us about the extreme conditions inside neutron stars? Neutron stars are the remnants of massive stars that have exploded in supernova. What's left behind is an ultra-dense core, packing the mass of our sun into a sphere roughly the size of a city. These stars spin incredibly fast, with some completing hundreds of rotations every second. Over time, their rotation slows down as they lose energy. However, occasionally, something unexpected happens, a glitch. During a glitch, the neutron star's rotation suddenly changes, either speeding up or slowing down in a way that defies our expectations. One leading theory suggests that these glitches are caused by the peculiar nature of matter inside neutron stars. Beneath their solid crust lies a superfluid, a state of matter that flows without friction. This superfluid is thought to rotate at a slightly different rate than the crust. When the two layers become misaligned, the superfluid can transfer angular momentum to the crust, causing the star's rotation to suddenly change. It's like a spinning ice skater pulling in their arms to speed up, but on a cosmic scale. Another possibility involves the star's magnetic field. Neutron stars have some of the strongest magnetic fields in the universe, and these fields can interact with the star's interior in complex ways. Some researchers believe that changes in the magnetic field could trigger shifts in the star's rotation, leading to glitches. However, the exact mechanisms remain a topic of debate, as these events are incredibly difficult to observe and study in detail. What makes neutron star glitches so fascinating is what they reveal about the extreme conditions inside these objects. The behavior of matter under such immense pressure and density is unlike anything we can replicate on Earth. By studying glitches, scientists can gain insights into the properties of superfluid matter, the strength of neutron star crusts, and even the nature of gravity itself. Each glitch is like a cosmic puzzle piece, helping us build a clearer picture of these enigmatic objects. As we continue to observe and analyze neutron star glitches, we're reminded of how much we still have to learn about the universe. These sudden, unpredictable changes challenge our understanding of physics and push the boundaries of what we thought was possible. They also highlight the incredible precision of nature, where even the smallest shifts can have profound implications. Next, we'll explore another cosmic mystery: ultra-high-energy cosmic rays, particles that travel through space with energies far beyond anything we can produce on Earth. What are these mysterious particles and where do they come from? Let's find out. Now, let's shift our focus to one of the most energetic and enigmatic phenomena in the cosmos: ultra-high-energy cosmic rays. These are not your ordinary particles. They are atomic nuclei traveling through space at nearly the speed of light, carrying energies millions of times greater than anything we can produce in our most advanced particle accelerators on Earth. Imagine a single particle with the energy of a fast-pitched baseball, but packed into something smaller than an atom. That's the scale we're talking about here. The mystery of ultra-high-energy cosmic rays begins with their origins. Despite decades of research, scientists still don't know exactly where these particles come from. They are so powerful that they must be produced by some of the most extreme events in the universe: supernova, black holes, or even collisions between galaxies. Yet, pinpointing their exact sources has proven to be a monumental challenge. One reason for this is that cosmic rays are charged particles. which means they are deflected by magnetic fields as they travel through space. By the time they reach us, their paths are so scrambled that tracing them back to their origins is like trying to follow a single raindrop in a thunderstorm. What makes these cosmic rays even more baffling is that they seem to break the rules of physics as we understand them. According to a principle known as the Greisen-Zatsepin Kuzmin limit or GZK limit, ultra-high-energy cosmic rays should lose energy as they travel through the cosmic microwave background radiation, the faint afterglow of the Big Bang. Yet, we've detected cosmic rays with energies far beyond what the GZK limit predicts. This raises a tantalizing question. Are there unknown processes or sources in the universe that can accelerate particles to such extraordinary energies? Or do we need to rethink our understanding of physics itself? One theory suggests that these cosmic rays might originate from active galactic nuclei, the incredibly energetic cores of galaxies powered by supermassive black holes. Another possibility is that they come from gamma-ray bursts, the most powerful explosions in the universe. Some researchers have even proposed that they could be the result of exotic phenomena, such as the decay of super-heavy dark matter particles. While these ideas are intriguing, none have been definitively proven, leaving the origins of ultra-high-energy cosmic rays shrouded in mystery. Studying these particles is no easy task. To detect them, scientists use vast arrays of detectors spread over large areas, such as the Pierre Auger Observatory in Argentina. These detectors look for the showers of secondary particles created when a cosmic ray collides with Earth's atmosphere. By analyzing these showers, researchers can estimate the energy and direction of the original cosmic ray. However, even with these advanced tools, the data remains sparse, and the puzzle of ultra-high-energy cosmic rays continues to challenge our understanding of the universe. What makes this mystery so compelling is what it reveals about the limits of our knowledge. Ultra-high-energy cosmic rays are a reminder that the universe is full of surprises, and that there are still phenomena out there that defy our current theories. They push us to ask deeper questions about the nature of matter, energy, and the forces that shape the cosmos. Each detection is a clue, a piece of a puzzle that could one day lead to a breakthrough in our understanding of the universe. As we ponder the origins of these cosmic rays, we're reminded of how much we still have to discover. The universe is a vast and complex place, and every mystery we solve seems to reveal new questions. Next, we'll turn our attention to another intriguing cosmic puzzle, the search for exomoons, moons orbiting planets beyond our solar system. What secrets might these distant worlds hold? Let's find out. Now, let's venture into the fascinating realm of exomoons, moons that orbit planets beyond our solar system. While we've discovered thousands of exoplanets over the past few decades, finding their moons has proven to be a much tougher challenge. Yet, the search for exomoons is more than just a scientific curiosity. It could hold the key to understanding the diversity of worlds in our galaxy and beyond. Detecting exomoons is no small feat. Unlike planets, which can be spotted through methods like the transit technique, where a planet passes in front of its star, causing a detectable dip in light, moons are much smaller and harder to observe. Their gravitational influence on their host planet is subtle, and their transits, if they occur, are often drowned out by the noise of the star's light. This makes identifying exomoons a bit like trying to spot a firefly next to a spotlight. Despite these challenges, scientists have developed innovative techniques to hunt for these elusive objects. One method involves looking for tiny wobbles in the timing of a planet's transit, which could indicate the gravitational tug of a moon. Another approach is to analyze the light curve of a star for secondary dips that might suggest a moon is also passing in front of it. While these methods are promising, they require incredibly precise measurements and a bit of luck. So far, only a handful of potential exomoon candidates have been identified, and none have been definitively confirmed. The significance of finding exomoons goes beyond just adding to our catalog of celestial objects. moons play a crucial role in shaping the environments of their host planets. For example, Jupiter's moon Europa is believed to harbor a subsurface ocean that could potentially support life. If exomoons with similar conditions exist, they could be prime candidates in the search for extraterrestrial life. Additionally, studying exomoons could help us better understand how planetary systems form and evolve, shedding light on the processes that shaped our own solar system. One of the most intriguing aspects of exomoons is their potential to host habitable environments. While many exoplanets orbit too close or too far from their stars to support liquid water, moons orbiting at the right distance could have stable climates and even atmospheres. This opens up the possibility of moon habitability, where life could thrive not on a planet but on one of its moons. Imagine a world where the night sky is dominated by a massive gas giant, with its own set of moons glowing in the distance, a truly alien landscape. As we continue to refine our detection methods and gather more data, the search for exomoons is poised to become one of the most exciting frontiers in astronomy. Each potential discovery brings us closer to understanding the full diversity of worlds in the universe and the potential for life beyond Earth. With every new observation, we're reminded that the cosmos is full of surprises waiting to be uncovered. Next, we'll turn our attention to another cosmic mystery that has captivated scientists and stargazers alike: the elusive Planet 9. Could this hidden giant be lurking in the outer reaches of our solar system? Let's explore the evidence and what it might mean for our understanding of the cosmos. Now, shifting our gaze closer to home, we delve into one of the most tantalizing mysteries within our own solar system: the Planet 9 hypothesis. This idea suggests that a massive, undiscovered planet could be lurking in the distant, icy reaches beyond Neptune, influencing the orbits of smaller objects in ways that defy explanation. But what exactly is the evidence for this hypothetical world, and why has it remained so elusive? The story of Planet 9 begins with a peculiar pattern observed in the orbits of distant icy bodies known as trans-Neptunian objects. These objects, which include dwarf planets like Sedna and others in the Kuiper belt, exhibit strange, clustered orbits that seem to align in a way that can't easily be explained by the known planets alone. Scientists noticed that these orbits appear to be tugged by something massive, something far beyond Neptune. This led to the hypothesis that a large, undiscovered planet, perhaps 10 times the mass of Earth, could be responsible for these gravitational anomalies. The search for Planet 9 is no simple task. Its proposed location is so far from the Sun, estimated to be between 300 and 700 times farther than Earth's distance, that it would reflect very little light, making it incredibly difficult to detect. To make matters more challenging, its orbit is thought to be highly elongated, meaning it could be anywhere along a vast, looping path that takes thousands of years to complete. This makes pinpointing its location a monumental challenge for astronomers. Despite these obstacles, the hunt for Planet 9 has spurred a wave of innovative techniques and technologies. Telescopes like the Subaru telescope in Hawaii and the Vera C. Rubin Observatory, currently under construction, are being used to scan the skies for this elusive giant. Researchers are also employing advanced computer simulations to narrow down the possible locations of Planet 9 based on the gravitational effects it would have on other objects. While no direct evidence has been found yet, the indirect clues continue to mount, keeping the hypothesis alive and fueling the curiosity of scientists and stargazers alike. The implications of discovering Planet 9 would be profound. Not only would it reshape our understanding of the solar system's architecture, but it could also provide insights into how planetary systems form and evolve. Some theories even suggest that Planet 9 could be a rogue planet, captured by the Sun's gravity long ago, adding another layer of intrigue to its story. If found, it would join the ranks of the solar system's major planets, becoming the first new addition since Neptune's discovery in 1846. As we continue to search for this hidden giant, the mystery of Planet 9 reminds us that even in our own cosmic backyard, there are still secrets waiting to be uncovered. Could this elusive world be out there, silently shaping the fates of distant objects? Only time and the relentless pursuit of science will tell. Next, we'll explore the broader implications of Planet 9 and how its potential discovery could change our understanding of the solar system and beyond. Now, let's consider what the discovery of Planet 9 could mean for our understanding of the solar system and beyond. If this hidden giant exists, its gravitational influence could explain more than just the odd orbits of distant icy bodies. It might also shed light on other cosmic mysteries that have puzzled astronomers for decades. For instance, some researchers speculate that Planet 9 could be the key to understanding why the solar system's plane is slightly tilted. This tilt, known as the obliquity of the ecliptic, has long been a subject of debate, and the presence of a massive, distant planet could provide the missing piece of the puzzle. Beyond its gravitational effects, Planet 9 could also offer clues about the early history of our solar system. One compelling theory suggests that it might not have formed in its current location at all. Instead, it could be a captured rogue planet, a world that was once adrift in interstellar space before being pulled into the Sun's gravitational embrace. If true, this would mean that Planet 9 is a cosmic interloper, a relic from another star system that now calls our solar system home. Such a discovery would not only rewrite the story of our planetary neighborhood, but also deepen our understanding of how planetary systems interact and evolve over time. The existence of Planet 9 could also have implications for the search for life beyond Earth. Its gravitational pull might have played a role in shaping the orbits of comets and asteroids, potentially influencing the delivery of water and organic molecules to the inner solar system billions of years ago. This raises the tantalizing possibility that Planet 9, though distant and icy, could have indirectly contributed to the conditions that made life on Earth possible. In this way, its discovery would connect the dots between the outer reaches of the solar system and the origins of life itself. Moreover, finding Planet 9 would underscore the idea that our solar system is far more dynamic and complex than we once thought. It would remind us that even in the seemingly quiet outskirts of our cosmic neighborhood, there are forces at work that we are only beginning to comprehend. The hunt for this elusive world is not just about adding another planet to the list, it's about uncovering the hidden mechanisms that govern the cosmos and reshaping our understanding of the universe's grand design. As we continue to search for Planet 9, its potential discovery serves as a powerful reminder of how much we still have to learn about the solar system. Whether it's a rogue planet, a long-lost sibling of the gas giants, or something entirely unexpected, its existence would open up new avenues of exploration and inspire a new generation of astronomers to probe the mysteries of the cosmos. The story of Planet 9 is far from over, and its implications could ripple far beyond the icy reaches of the outer solar system, challenging us to rethink what we know about the universe and our place within it. As we reach the end of our journey through the 25 unexplained space anomalies, one thing becomes abundantly clear: the universe is far more mysterious and complex than we can ever fully grasp. From the baffling dark flow phenomenon to the elusive Planet 9, each anomaly challenges our understanding of the cosmos and reminds us how much we still have to discover. These mysteries are not just scientific puzzles, they are invitations to explore, to question, and to dream. They push the boundaries of our knowledge and inspire us to look deeper into the vast expanse of space where countless secrets remain hidden. The quest to unravel these cosmic enigmas is far from over. With every new discovery, we uncover more questions than answers, and that's what makes the study of space so endlessly fascinating. Whether it's the strange behavior of Tabby's star, the eerie silence of the Fermi paradox, or the unexplained glow of the galactic center excess, each anomaly reminds us that the universe is a place of wonder, filled with phenomena that defy our current understanding. And as we continue to probe these mysteries, we inch closer to unlocking the secrets of the cosmos, one anomaly at a time. So, what do you think lies beyond the edge of our observable universe? Could there be forces or structures we've yet to imagine, shaping the fabric of reality in ways we can't yet comprehend? The answers may be out there, waiting for us to find them. If you've enjoyed this exploration of the universe's greatest mysteries, don't forget to share your thoughts in the comments below. What anomaly fascinates you the most? And if you're eager for more cosmic discoveries, hit that subscribe button and ring the notification bell so you never miss out on the latest insights into the wonders of space. The universe is full of secrets. Let's uncover them